Good day, everyone. This is Dr. Soper here, and today I'll be discussing the third topic in our series of lessons on information privacy and security, with today's topic focusing on software program security. To begin, I'd like to emphasize that protecting software programs lies at the very heart of computer security. This statement does not apply exclusively to system software, but rather applies to all kinds of software programs, including applications, operating systems, database management systems, software programs that run within network hardware, software programs that are embedded within intelligent circuitry, and so forth. Earlier in our series of lessons on information privacy and security, I introduced the concept of the CIA security triad, that is, confidentiality, integrity, and availability. Note that in the context of software program security, a software program can be considered secure if it enforces or provides for these three elements of the security triad. Further, it's important to realize that ensuring software program security is a very difficult task. There are at least 4 reasons for this. First, implementing program security often causes problems with respect to the usefulness or performance of a software program. Second, and this is a critically important point to understand, it is essentially impossible to ensure that a software program does only what it is designed to do and nothing more. Although it is relatively straightforward to determine whether a program can perform all of the tasks it was designed to perform, guaranteeing that the program will perform only those tasks and that it cannot perform any other tasks is virtually impossible. Third, the techniques that are used in programming and software engineering are changing and evolving faster than computer security techniques. And this means that computer security methods will always lag behind contemporary programming and software engineering methods. Finally, software program security is difficult because even a single flaw can be catastrophic from a security perspective. A software program may implement 1,000 different functions, and 999 of those functions might be perfectly secure. The one function which contains a security flaw, however, might still make the user or the entire system susceptible to a disastrous security attack. Before we proceed further, I would like to briefly discuss a few terms related to fault tolerance. First among these is the term error. In the context of fault tolerance, an error is a mistake in a software program that may lead to a fault. A fault, then, is a situation in which the behavior of a computer program deviates from its intended behavior. If left unchecked, a fault can lead to a failure, which is a system malfunction that is caused by a fault. In order to clarify the relationship among errors, faults, and failures, consider the following example. Imagine that a programmer makes an error in her code. When the code is executed, the error generates a buffer overflow fault. The buffer overflow fault then causes the system to crash. That is, it causes a failure. Note that we can classify faults into 2 separate groups according to the manner and frequency with which they appear. Permanent faults are those faults which occur every time a program is executed, while transient faults are those faults which occur only intermittently. Transient faults are, of course, almost always much more difficult to diagnose than permanent faults. Next, I'd like to talk about a series of common vulnerabilities that can appear within software programs. First among these is a vulnerability known as incomplete mediation. Incomplete mediation, or incomplete checking, is a situation in which sensitive data exist in an exposed, uncontrolled condition and are hence subject to manipulation by a malicious user. It's important to realize that incomplete mediation is usually inadvertent, that is, it is usually non-malicious, but it nevertheless can have serious security consequences for a software program. As an example of incomplete mediation, Imagine that this URL is generated by a client's browser during an online purchase. Notice that sensitive information, including the customer ID, the part number, the quantity ordered, the item price, the shipping cost, and the purchase total, are all contained in the URL query string. Now imagine that a malicious user edits the URL directly, changing the item price and the total cost as shown here. When the user instructs her web browser to load this URL, the maliciously modified values are sent to the server. If the server fails to verify the price of the item, then it will accept $25 as the total cost, and including shipping, the user would have purchased 20 of item 55A for just $25, as opposed to the legitimate total of $205. Unchecked or unvalidated data therefore represent a serious vulnerability to computer software programs. To help eliminate such vulnerabilities, it is necessary to anticipate incomplete mediation problems and design software programs such that they rigorously check and validate input data. This can be accomplished in part by relying upon the server to compute sensitive values, such as the total amount due for an online purchase. Another strategy is to use software or website development controls, such as drop-down boxes, radio buttons, and calendar controls, that prevent users from editing input values directly. Finally, it is critically important to check the validity of data values after they are received from the client. From an information security perspective, it is very poor practice to rely exclusively on client-side validation. The next common software program vulnerability that I would like to discuss is known as a race condition, or a serialization flaw. A race condition occurs when two concurrently executing processes produce incorrect computational results. As an example of a race condition, consider this figure, which represents a poorly designed airline reservation system. In the figure, imagine that we have two web customers, A and B, who are trying to book a seat on a specific flight. Further, let's imagine that there is only one seat remaining, and that both A and B are attempting to book the one remaining seat at nearly the same time. The race condition begins when A asks the reservation system if any seats for the flight are available. The reservation system responds yes, because one seat remains for the flight. At this point, B also asks the reservation system if any seats for the flight are available. Again, the reservation system responds yes, because one seat remains for the flight. If both A and B then proceed to book the seat, and the reservation system has no mechanism for preventing a race condition, then the airline would have sold the same seat to two different people, which would obviously be problematical in a number of different ways. The next common software program vulnerability that I would like to discuss is known as a time of check to time of use, or TOCTTOU vulnerability. This vulnerability occurs when data values are changed between the time that the software program checks or validates the data values and the time that the program actually uses those values to perform a task. As a non-computational example of this vulnerability, imagine that a person is interested in purchasing an expensive item such as a designer handbag or a luxury watch. The salesperson allows the buyer to examine a real designer handbag or a real luxury watch, and when the buyer pays for the item, the salesperson surreptitiously switches the real designer handbag or luxury watch for one that is fake. The key to preventing these time of check to time of use vulnerabilities is for programmers to be aware of the time lags that can occur in program execution between the time when data values are checked and the time that they are actually used. If necessary, digital signatures, certificates, or encryption can be used to lock data values after they have been validated, such that it becomes impossible for a malicious party to modify those values before they are actually used by the software program. The final common software program vulnerability that I would like to discuss is known as an undocumented access point, also known as a backdoor or a trapdoor. This vulnerability occurs when a method of accessing or manipulating internal values within a software program exists that circumvents or sidesteps the program's usual security mechanisms. Undocumented access points are often artifacts of the system development process. It is quite common for programmers to create these backdoors in order to facilitate the testing or debugging of the program while it is still under development. Unless these undocumented access points are removed from the final version of the program, however, they can cause very serious problems from the perspective of program security. In general, flaws in software programs can be classified into two broad categories: intentional flaws and unintentional or inadvertent flaws. Intentional flaws are those flaws which are introduced into the software program on purpose by developers. These intentional flaws can be either malicious or non-malicious, depending upon whether the intent of the developer is to cause harm or not. Unintentional or inadvertent flaws, by contrast, are not introduced into the software program on purpose, but nevertheless exist and therefore represent a security risk. It is important to note that inadvertent flaws are not only commonly more numerous than intentional flaws, but they also commonly cause just as much damage as intentional flaws. Inadvertent software program flaws can exist in many forms, including validation errors, domain errors, serialization or aliasing errors, inadequate identification and authentication, boundary condition violations, or any number of other exploitable logic errors. Next, I'd like to discuss a countermeasure which has been used for many decades in an effort to address software program flaws, but which over time has come to be recognized by many security experts as largely ineffective. This countermeasure, known as penetrate and patch, is a method of evaluating the security of a software program in which a specialized team, known as a red team or a tiger team, intentionally tries to crack or break the software program. The theory underlying this approach is that if a program is able to withstand the attacks of the tiger team, then the security of the program must be reasonably sound. In reality, however, this theory is rarely true. One of the reasons for the failure of the penetrate and patch approach is that the developers of a software program will often try to quickly fix the problems that have been discovered by the tiger team. Put simply, applying quick patches to program flaws often causes new faults to emerge. This is commonly due to pressure or stress that is placed on developers due to the discovery of a flaw. When a flaw is detected, software developers often feel pressure to focus on the fault itself rather than the broader context in which the fault appears. Further, quick patches often have non-obvious side effects. A seemingly minor change in one part of the system, for example, may cause cascading problems which have negative implications for other parts of the system. Finally, the security overhead that is required in order to patch a program fault may not be allowed in light of a system's performance requirements. For these reasons, the penetrate and patch method should be abandoned in favor of a more holistic approach, which seeks to control software program threats by considering security issues throughout the entire software development process. As a process, developing a software program involves many different tasks, including requirements analysis, design, implementation, testing, review, documentation, deployment, maintenance, and so forth. Security concerns permeate and interconnect all of these tasks, and therefore must be actively considered throughout each phase of the software development lifecycle. Also note that because these tasks are rarely carried out by a single person, the social relationships that exist among the developers of a software program can have substantial impacts on the program's security. In light of the interconnected nature of the tasks that must be carried out in order to design and implement a software program, controlling against program threats can be most effectively accomplished by considering security issues on an ongoing basis throughout the entire software development process. Put another way, rather than waiting until the testing phase of the software development lifecycle before efforts are undertaken to identify and correct flaws in a software program, a much more effective strategy toward ensuring program security is to actively think about and implement security mechanisms and controls throughout each phase of the software development lifecycle. One of the ways of enhancing the security profile of a software program is to design the program on the basis of modularity. Modular software programs are composed of many subcomponents called modules, which can be defined on either a logical or a functional basis. Each of these modules should be designed to meet 4 criteria. First, each module should perform just one function. Second, each module should be small. Third, each module should be as simple as possible. And finally, each module should be able to perform the task for which it was designed in isolation. By building software programs using a set of small, independent modules, the likelihood of encountering security flaws is lessened dramatically because it makes the software code easier to maintain and the program easier to understand. A modular design also enables each module to be tested and studied in isolation, thus allowing the cause of a security flaw to be more easily identified. One way of thinking about modularity in software program design is to consider an analogy with a jigsaw puzzle. Just as a jigsaw puzzle is comprised of a collection of independent, interconnected pieces, so too is a modular software program comprised of a collection of independent, interconnected modules. What's more, each module is simple, small, and understandable, just like each individual piece in a jigsaw puzzle. When the modules are assembled in a proper fashion, the result is a complete software program. Other software design practices that can be used to enhance program security include both encapsulation and information hiding. Encapsulation refers to a programming practice in which a module's inner workings are hidden from other modules. Consider, for example, a situation in which an encapsulated module is designed to compute a specific value for a managerial report. By preventing the other modules which comprise the program from knowing how the value for the report is actually computed, security is enhanced, since any weaknesses that might exist within the module are effectively hidden from the rest of the program. The practice of information hiding is similar to encapsulation, but information hiding refers specifically to the data values that are stored within and used by an encapsulated module. Put another way, information hiding refers to a software design practice in which the actual variables or data values that support an encapsulated module's internal computations are not visible or accessible to other modules within the program. Additional strategies that can be used during the software development process to control against program threats include both mutual suspicion and confinement. As a philosophical design principle, mutual suspicion proposes that when it is necessary for two software programs to interact, each program should be suspicious of the other. That is, a software program should never fully trust another program. Instead, software programs should protect themselves by granting only limited access to other programs and by rigorously checking or validating any input values that are being supplied by other programs. Confinement, on the other hand, refers to a computing principle in which an operating system actively seeks to protect the system and other software programs by isolating and confining any programs that are suspected of being untrustworthy. Under this model, a software program which has been confined by the operating system is granted only very limited access to system resources and data. Examples of software programs that are strong candidates for confinement by an operating system include both Adobe Flash applications and Java applets that are downloaded by a user's browser as the user navigates the web. Since these applications might be written by anyone, it makes sense from a security perspective that they should be confined by the operating system. As a user of software programs, it is important for you to realize that a security danger exists when you adopt too many technologies from the same vendor. The reason for this is that a vendor will commonly design its software programs such that the programs easily integrate and communicate with one another. Highly integrated systems, however, enable potential security flaws to easily cascade from program to program. For example, Microsoft Internet Explorer and all of the Microsoft Office programs are highly integrated not only with each other but also with the Windows operating system. A serious security flaw in any one of these programs, then, might be able to easily cascade to the others because of their high degree of integration. From a security perspective, it is much less likely that a security flaw in one program will be able to impact other programs if the flawed program is not highly integrated with those other programs. This is what is meant when we speak of genetic diversity in the context of computer security. Here we see how security issues can be considered throughout each phase of the software development process with a view toward producing secure software. Beginning in the requirements analysis phase, we should consider the ways in which the system might be abused. As we proceed through the process of designing the program, potential threats, vulnerabilities, and countermeasures should be an active part of our calculus. During implementation and testing, we should use development tools, test plans, and strategies such as code reviews, which are supportive of secure software development. Finally, during the acceptance and maintenance phases, we should consider residual risks associated with the software program, and we should seek to mitigate risk and further enhance the program's security by gathering feedback and learning from our mistakes. One of the strategies that can be used to improve security during the actual coding of a software program is to conduct peer reviews. In the context of software development, a peer review is simply a process in which the computer code that is written by one programmer is reviewed by one or more other programmers with a view toward identifying and eliminating security flaws. These security flaws, of course, might be either malicious or non-malicious. When writing a software program, computer programmers can often become blind to their own mistakes. Having another person review their code can help a programmer to ensure that any unintentional security flaws in his or her work will be detected before they become a problem. Conducting a peer review can also greatly limit the possibility of intentional, malicious security flaws becoming part of the software program. First, unless there is collusion among all of the programmers, it is much more difficult for a programmer to embed a malicious security flaw in the software program if her work will be reviewed by another programmer. Further, if a programmer knows that her code will be reviewed by another programmer, the peer review process itself provides a disincentive for the programmer to attempt to embed a malicious security flaw within the software program. Although in an ideal world our software programs would be entirely free from faults, in reality we must expect that our programs will fail from time to time. The reason for this is that it is simply not feasible to test a software program with every possible combination of input values. Consider, for example, even a very simple software program such as a calculator application. Despite the comparative simplicity of such an application, we could supply it with an almost infinite variety of input values, thus making exhaustive testing essentially impossible. Since it is simply not feasible to test a software program using every possible combination of input values, we must instead adopt a strategy in which we design our software to anticipate and detect fault conditions and handle them elegantly as they arise. This philosophy is now well established in the computing world, and virtually all modern programming languages provide mechanisms for trapping and handling errors. As a general set of guidelines, software programs should be designed such that when an error occurs, any disruptions to the user caused by that error should be minimized. Additionally, the damage caused by a fault should be isolated and contained, thus preventing that damage from spreading to other parts of the program or to the system as a whole. Because of the complex interconnections among the modules which together comprise a software program, changes made to one part of a program can often have unintentional security consequences for other parts of the program. For this reason, it is important to keep track of who is making changes to which parts of the program during the software development process, and this is accomplished using a strategy known as configuration management. If a modification to a software program has unanticipated or undesirable security consequences, then configuration management will allow those undesirable changes to be rolled back as necessary. Adopting a configuration management strategy is particularly important for large software development projects and for the development of open source software programs. Many programmers simultaneously contribute to such projects, and because of the large scope of these programs, it is not feasible for a single programmer to understand the code for the entire project in detail. It is therefore difficult for a programmer to fully comprehend the security implications of a code modification, thus necessitating the adoption of a configuration management strategy. In addition to the security controls discussed previously, there are several other security controls which can be implemented during the software development process in order to help ensure that a software program is secure. Hazard analysis, for example, can be used to reveal hazardous system states. By relying upon a set of systematic techniques which commonly involve the development of hazard lists and what-if scenarios, the software development team can use hazard analysis to identify security flaws which might otherwise go unnoticed. If used properly, prediction can also be an effective security control. By predicting which security problems are most dangerous or most likely to occur, the software development team can manage risk by targeting its limited resources to where they will be most useful. Before deploying a system, the software development team can perform a static analysis in which the program's code and design specifications are examined for evidence of potential security threats. The focus of such analyses is almost always on a software program's control flows, and data structures. Finally, it is critical that a software development team analyze past mistakes. By documenting and studying security breaches, we can learn to avoid making the same mistakes in the future. Analyzing past mistakes requires that the software development team keep a record of its design decisions so that those design decisions can be reviewed whenever a security breach is identified. Prior to being deployed, it is critical for software programs to be extensively tested in order to ensure quality, stability, and accuracy. For this purpose, at least 10 different varieties of software testing have been defined. First among these is unit testing, in which the functionality and behavior of each component that comprises the program is tested in isolation. Following unit testing, we can perform integration testing, the purpose of which is to evaluate the extent to which the various components that comprise the software program interact with one another as intended. Following integration testing, we can perform function testing, the purpose of which is to evaluate the ability of a system to perform the functions for which it was designed. After successfully completing unit testing, integration testing, and function testing, we may engage in performance testing, in which we evaluate the ability of the system to achieve the performance standards for which it was designed. With a view toward ensuring customer satisfaction, we may subject a software program to acceptance testing, in which we evaluate the program's capabilities against the requirements that were provided by the customer. It is also important to realize that the final production environment for a software program often differs from its development environment, and for that reason we should conduct installation testing, in which we evaluate whether a program functions correctly after being installed in its final production environment. With respect to the specific methods of testing that we have at our disposal, we might perform black box testing, clear box or white box testing, or penetration testing. Black box testing is a testing strategy in which we do not consider the internal workings of a software program, but rather are interested in ensuring that the program generates correct output values in light of a known set of input values. By contrast, in clear box testing, we evaluate a program based on our knowledge of its internal structure or design. Another tool in our testing arsenal is penetration testing, in which we evaluate the ability of a program to withstand attacks by subjecting it to a series of simulated attacks from both external and internal sources. Finally, if we make a modification to a software program, we should subject the program to regression testing, the purpose of which is to evaluate whether all of the program's functions are still working properly after a change has been made. Unfortunately, despite our best efforts, no combination of development controls is able to guarantee that a software program will be perfectly secure. Nevertheless, it is necessary for us to do our best to make software programs as secure as possible by actively considering security issues throughout the design, development, and implementation of our software programs. Fostering an organizational culture which supports the creation of secure and high-quality software requires that we establish and enforce a collection of software development standards. Possibilities in this regard include design standards, documentation standards, programming standards, testing standards, or configuration management standards. In the end, however, implementing software development standards will not in and of itself be sufficient to ensure the production of secure and high-quality software. Instead, we must create an organizational climate which supports identifying and learning from mistakes, and which uses that knowledge to refine the organization's software development standards in the spirit of continual improvement. In this way, an organization will give itself the best chance possible of producing secure, stable, and high-quality software products. Well, my friends, thus ends our overview of software program security. I hope that you learned something interesting in this lesson, and until next time, have a great day.